Hi, everybody. Thanks for coming. And I just wanted to say a warm thank you to all the kind words which people have sent me. And I should also say thanks a million to Shu Yu, who's been able to set up everything here. And she will, as we did last Friday, she will be in the class, whereas I will try to answer people online. But for those of you in the class, if you want to, you can also log in online with a Zoom link, which we have, and then you can ask questions. I see there are some people online already, and you can just ask questions wherever you want. I will be around till we are done, roughly 5 o'clock, if people wish to hang around. And then on Monday, we are back in the normal situation. So Monday, we will have the lecture in the Zoom, in a STEM building as before. I wanted just to sneak in some 10 minutes with a hint and perhaps a kind of guidance when it comes to exercises 5 and exercises 6 in the present homework. Now, one thing which I wanted to say first is that if you're looking after the Jupyter notebooks of the lectures, so one thing you can do, if you click on the link which you see up here, then you will get to the overview here. And in this overview, you can find the same material as a PDF, different HTML formats, or as a Jupyter notebook. So that's one site where you can get all the information. And if you scroll down this site, just to repeat these messages, I hope you don't get annoyed by that, you will also find the exercises in different formats. But if you wish to, you can obviously clone the whole repository by just clicking on code here. And then if you have it on your laptops or PCs, you can always get a weekly update by doing a Git pull. Now, the files are also under this folder. If you go to this folder pub here, and you look at the present week, so this will be week 5. And if you go into week 5, you can go directly and fetch the files which you're interested in. So like if you click on this link, you will find the Jupyter notebook, which I'm going to show pretty soon. So that's just about the material. Now for the exercise this week, this exercise 5, and 6, if we just take a look at the exercise set, you will find the solutions to these exercises in the for the first part, the paper and pencil part, which I'm just going to repeat quickly. You will find the solution to that one in the lecture slides for the second week. At the end of that, I'm going to point that to you. And then for the last one, you will actually find basically an approach to the solution in the slides for this week. So I'm just trying to just redirect your reading in case you get stuck with the numerical exercises, but also the paper and pencil exercise. Now, when it comes to the numerical exercise, I know that there are many of you who have not taken CMSE 201. There are some of you have taken it in parallel. Feel free to use the programs which you see in the lecture notes as a starting point for writing your codes. In the beginning, you have an almost complete solution of the exercises, but later you will have to keep adding elements. So hopefully these programs, which I've written in a pretty simple and straightforward way, they can be of some use for you guys if you want to. I'm obviously going to record this session. I will put it online immediately after we're done. So in case you didn't get all the messages, you can always look back at it. So one thing which I wanted to do first is just to slow down the pace a little bit and just jump into the tablet and the whiteboard and just take a quick look at the problem which we have in exercise 5. So as I said, we have been looking at this exercise 5 in the week, in the second week, which we had. But so just a quick moment. So what we need to do now when we analyze a problem is to set up the initial conditions in this exercise. So if we are dealing with a problem in 2 dimensions, which is the case in problem 6, the numerical one, then we can set up the initial position in terms of an X component and a Y component. And then we have the initial velocity. And in this specific exercise, we have only in exercise 5, we have only an object which falls in one dimension. The thing which we need to do also is to analyze the forces which are at play. And one of the forces is the gravitational force, and that gives us G equal to minus mg multiplied with J. And then we also have this air resistance, and that is modeled with a constant, which is often called a drag constant, which is an experimental quantity. So we would call this an F of D, and this is given by minus D times the velocity. This is the velocity vector. This is a general case, and multiplied with the absolute value of the velocity. Now, for this particular case here, we are just looking at things in the y direction. So in this exercise, in exercise 5, this simply reduces to an acceleration in the y direction, which is given by minus G. And since this force points now, the air resistance points upward, this is given by D, but now we don't need the absolute value of the velocity because we're just in one dimension. And then we would just have V squared. And I'm skipping the time dependence. But if we go to the exercise 6, then we need to add the gravitational force, and we would need to add the x direction. So if we look at exercise 6, then we have ax, which is given by this minus d, and then this is divided by m. Actually, I forgot to divide by m here because we divide with the mass, and we have d divided by m, and then we have the velocity component in the x direction multiplied with the absolute value of the velocity. And then when we look at the y direction, we would have minus g. But now since this air resistance is pointing upwards against the direction of the motion, we are thinking of this object falling down, we would have a d divided by m, and then we would have a v of y, and then we take the absolute value of the velocity. And this absolute value is something which in our case, since we're just in 2 dimensions, this will be given by Vx squared plus Vy squared. Now, the case in 1 dimension is something which we can solve analytically, we can integrate easily, whereas the case in 2 dimensions is a case which we can only solve numerically. I may be wrong here, perhaps one can find an analytical solution, but I was not brave enough to find an analytical solution. And the main reason for that is that in the x and the y direction, there is a dependence on both v of x and v of y. So that means that we cannot have 2 decoupled directions which don't depend on each other. So let me go back to the Jupyter notebooks now. So just the reason why I did this is that it's important for us to analyze the problem. So one thing is to find the initial conditions, and the other is to find the forces which are at play. And this is the way we will proceed essentially throughout the rest of the semester when we are setting up a physics problem. So I'm going to switch back to the Jupyter notebooks. And what I wanted to show you first is the material from the second week, which we went through. So in this second week, not that one, but it should be this week. So this is something which we did on Wednesday, the 18th and January the 20th. So if you scroll down for that particular week, and you just go down on the slides here, then you will find the discussions about the falling objects as we discussed. And there you will find the solution to this specific problem here. And it deals about the integration of the equations. We started with a falling object without any air resistance, and then we got this simple expression, which you probably have seen many, many times before. And then we included air resistance. And in that specific case, you can find the derivation of the analytical solution here. So this constant d here has actually absorbed the mass here. So this is a d which is slightly different from the one where we set up the force actually. So what you can do then, if you follow these, or if you look into Taylor's textbook, you will essentially find the solution to this problem here. So you would integrate up when we put the velocity to 0, and we have a final velocity, we integrate from time t0 equal 0 up to a final time. And then we can find the solution for the velocity as a function of time, and this is the solution. And then you can integrate up again, and in this case, you can do it by paper and pencil, or it's a little bit trickier, you would need to look up some mathematical formula for integrals, or alternatively, you can use symbolic Python or Mathematica. So in this course, we leave it to you to decide which method you want to use to integrate. So this is a solution we are going to compare the numerical exercises with. So you find actually, and again, I hope you don't get offended if I present most of the solutions like this, but this is a way to get you all started. And if you now go into the slides for this week, so that means the material which we have gone through now, we discussed the work energy theorem and conservative forces, energy momentum, energy and angular momentum conservation, etc., etc. But if you go at the end, towards the end of the slides, and this is the material I wanted to show you, if we just scroll down here, then you will find a discussion of exercise 6. And you have now found in the paper and pencil exercise, you have set up the forces which are at play. And in this case now, we are just using Newton's method, and we discretize, we find a time step, delta t. And if we want to compare the numerical exercise with exercise 5, then we obviously have to use the same initial velocities, which are not those which we have here. So you have to decide, based on the initial velocities, what kind of problem you want to look at. So Newton's method, no, sorry, not Newton's method, but Euler's method is very easy to implement. So you would have a loop over the time steps after you have defined all the constants. You update velocities and positions, and then you can calculate the new acceleration, and then you would repeat these steps for each time step. And in this specific case, I have a general program here, and this general program starts with defining constants. As you can see, I define the acceleration of the gravity constant. I define this parameter, which is dependent on temperature, on the type of object which is falling, etc., etc. The mass of the object, I define a delta t and a final t. And I set also up my constant. This is a constant vt, which you can use to define the final time, actually, if it's falling in just in the y direction. And then I define the arrays. So in this case, I have a kind of simple brute force approach where I do an array for the velocity in the y direction, one for the position in the y direction, one for the velocity in the x direction, and one for the velocity, now the position in the x direction. And here you see you can play around with initial conditions. And what I'm also doing here is to plug in the analytical solution. And so these are all the initial conditions which you can set up. And the program here is a program which allows you to study this problem in 2 dimensions or 1 dimensions if you put v of x equal to 0 and x, the initial position, to 0. So this is also a useful check that your program is running correctly. So what you need, and as we have been discussing again and again in these weeks, as soon as you have fixed the acceleration, you have the basic ingredients for solving most of the problems in this course. And the only thing you need to do is to update the velocities in the x directions, position in the x direction, velocity in the y direction, and the position in the y direction. And then we can compare with the analytic solution, which I'm just plugging in here. And then you can plot the relative error if you want to, or just plot the analytical solution with the numerical one. So if we run this code now, so let's try to do that. So what you would see then is now the difference between, or the relative error between the analytical solution and the numerical one. And Euler's method is not the best one. We can obviously increase the number of integration points. And here you see this object, which now is falling in the y direction. So nothing happens in the x directions, as you can see here, which is expected because we put the initial velocities and positions in the x direction to be 0. And you see now that the object is simply falling in the y direction as a function of time. And this is the velocity in the y direction, which obviously, as it keeps falling, it gains more and more velocity. And it's pointing downwards. And that's why we have a minus sign. And you see in the x-axis, nothing happens. For x and v of x, there's nothing, which is as expected. Now, this program, you can easily change the situation because we have now a general code which allows us to solve the problem in 2 dimensions. So I could say, okay, let me give the object an initial velocity. And I could even give it an initial position. Suppose I just put it at 2 meters, something like this. And then you can solve the equations again. And in this case, now you see that this was the initial velocity, the initial position in the x direction. And now something happens in the x direction as well. And so after some time steps, up to this final time, 1.4, you can let it run longer. It has moved something like 8.6 meters. It keeps falling. And then it has a velocity in the x direction, which obviously is diminishing because we have an air resistance in the x direction. And now things look slightly different. So you can always decide. So if you have a velocity which now points in the negative x direction, you can do that. So this velocity is pointing in a positive x direction, but you could give it a velocity which goes in the negative x direction. You can give it an initial velocity in the y direction. So it could start with 6 meters per second, and then you could let it fall. And now you will see that the velocity here, when it has a velocity here, it has to go up, and then it starts falling again. So this is the kind of games you can play now and develop your physics insights. Now, this code, which you see here, in the next homework, in homework 4, the only thing you need to add to the forces here, or the accelerations, will be an acceleration which comes from a normal force from the ground. So your object, this ball, will then bounce up and down. And that makes the motion a little bit more realistic. So I'm going to end here with the more compact version of the same code. And this is a kind of Python option, which gives us a code which is perhaps easier and closer to the mathematics which we are looking at. So in this case, we are defining a matrix, a 2-dimensional array, where in the first dimension, we have the number of time steps, which is, you see, defined here. I define time here to contain now a certain amount of time steps. And then I have 2 elements in the second dimension here, and that could be the x and the y direction. And you see now when I'm defining R0, I'm defining the initial velocity, the initial position in the x direction, and the initial velocity in the the initial position in the y direction. This is now the initial velocity in the x direction and the initial velocity in the y direction. And this simply says now that at time 0, it's equal to R0 for velocity and position. Now this gives a much more compact code, but now I have to be a little bit careful because these are vectors now. So I actually have to take the inner product of the vector. So I take the square root and the sum. So that means it sums the x component and the y component. So if you're not too familiar with this kind of vector matrix way of thinking, if you haven't taken a course in linear algebra, you can always go back to the code which you see here, where you explicitly write out the x and the y components. If you're more familiar with that, this kind of compact notation makes the code much more compact, closer to the mathematics which we have. And you see now that I'm just setting up the force without specifying now, this is implicitly setting up the x and the y directions. And you can see also that I can set up the gravitational force because I have defined my gravitational force here as you can see here. So this is my gravitational force, and it simply has the component in the x direction and a component in the y direction. And it has a minus, and it's multiplied with g. So that means that I can actually set up the force like this, and then I can set up my acceleration like this, the net force divided by m. So I need to calculate the absolute value of the velocity, obviously, but this gives you a much more compact way of coding it, and it's closer to the mathematical expressions. So if you're more familiar with this way of coding, feel free to use this code as well. And this is where I'm going to stop. Now, feel free to ask questions. I see that there are people online. For those of you online, I will just stay in here and I will answer your questions. But if somebody in the audience is not able to have time to answer the questions, feel free to actually log in and ask questions. Okay, so I'm going to stop the recording now, and now Shuju will be in the audience, and Abby comes at 4 o'clock, and next Monday we are just back all in the STEM building. So there's no Zoom session. Actually, there will be a Zoom session for those of you who cannot come in person, but we will have in-person lecture on Monday. Okay, I'm going to stop the recording, and feel free to ask questions, and yeah, just keep working on the exercises.